Hey guys, this is Mrs. Lyons, and this video is going to walk you through the parts of a heating curve. I'm going to start with just a blank piece of graph paper. We're going to construct a heating curve of water, and we're going to talk about what each segment means. Okay, so the first thing that's really important whenever you make a graph is to give your graph a title and label the axes with what is being observed and the units that we're using. Okay, so I'm just going to name this graph heating curve of water. All right, the units on my y-axis are going to be degrees Celsius, and the units on my x-axis are going to be heat added, and my units would be joules. Now, I'm not going to put units on my x-axis. I'm not going to put segments just because I'm showing you the shape and what a heating curve shows us. It's not going to actually be the exact heating curve that you would develop in the lab. Okay, so if we're looking at a heating curve of water, we want to observe all three states of matter: solid, liquid, gas. Okay, so a couple of things that are important with water. Okay, we know, and we're going to observe solid, liquid, and gas phase. Okay, and we are also going to observe the transition between solid and liquid, okay, which would be melting, and the transition between liquid and gas, which would be boiling. Okay, and I am going to, when I get my graph starting to draw, I'm going to identify, I'm going to highlight the different states of matter with colors. And I'm going to use the orange for the gas phase. Just broke my marker. Purple for the liquid phase, and blue for the solid phase. Okay, just so that when I get done, we'll kind of be able to look at it and see what we've got. Okay, so what we're going to do, we know that water melts or freezes at 0 degrees Celsius. We know it boils at 100 degrees Celsius. So those are going to be two important spots on my graph. Okay, so I'm going to start my graph below 0, and I'm going to end it above 100, so we can actually see the whole process as water heats. So what I'm going to do, I'm going to start at about, I'm going to say minus 30 degrees Celsius. And then we're going to observe what happens as water heats up from ice, the solid, to liquid water, to finally steam or gas, water in the gas phase. All right, so I'm going to go from about minus 30 to 140 on my graph. Okay, so here's what we would observe. We would first observe, if we start below 0, okay, we're going to start with our ice at minus 30. So it's going to be completely solid at that point. And what's going to happen on our graph as we add heat is that solid ice, it's going to remain solid. It can't melt until it gets to 0 degrees Celsius. Okay, so what we have here is we just have we just have water as solid. Now, if I were to draw a picture of this, so let me draw a little container. If I were to draw a picture of what the solid looks like, I would draw it with the particles very organized, very close together, with very, very little movement taking place. And notice that my particles also don't take the shape of their container. It's ice. It's a solid block. Okay. So what's happening as we move from minus 30 to 0 degrees Celsius is the kinetic energy, Ke, kinetic energy, of the water molecules. The kinetic energy is going up as we raise the temperature. We've said temperature and kinetic energy kind of go hand in hand. Okay, and as we raise the temperature, the kinetic energy increases. Now, with a solid, that might be kind of hard to think about, because we've said in the solid state, the particles really don't move much. Okay, so in the solid state, the particles are just kind of vibrating. And as we go from minus 30 to 0 degrees, they start vibrating a little bit more and a little bit more. When we reach 0 degrees Celsius, that's the melting point of water, what's going to happen is, instead of continuing to move up, the temperature is going to be held constant for a while. Okay, and on our graph, we're going to see a plateau. And along this plateau, what we are seeing is not only solid ice, but we're also seeing that our water, our H2O, is gradually turning to liquid. So along that plateau, we have both solid and liquid present, and the substance is melting. Okay, so it's going from a solid to a liquid. Okay, and that energy, it's not raising the temperature, it's not increasing the kinetic energy anymore, it's increasing the potential energy. PE, potential energy, is increasing along the plateaus. So here's a way to remember this. If you think about P, okay, P stands for three things on our heating curve. It stands for plateau, a flat spot. It stands for phase change, and it stands for increasing potential energy. Okay, so if that helps you, those three P's happen along the plateau. Okay, so along this plateau, our temperature remains at 0 degrees. What's happening to these particles is they're moving, and they're moving just a little bit until they break free from each other just enough so that they're in the solid phase. Or excuse me, they're in the liquid phase. Okay, so what happens now, once we get all of our molecules converted from solid to liquid, our temperature is going to start to climb again. And our temperature is going to climb from 0 degrees Celsius to 100 degrees Celsius. And at this point along our graph, all we have is liquid water. Okay, and that liquid water is just heating up. Okay, it's heating up, and because the kinetic energy is increasing. Okay, so along the slope, the kinetic energy is increasing. Now, if I were to draw a picture of this, okay, I've got my container still. What we're going to see in our container is, instead of the particles being tightly packed and uniform, we know that when water forms, the particles break through those intermolecular forces just a little bit, and they start moving around randomly. And we say this is why liquids and gases can flow, because there's a little bit more space in between the molecules. Now, notice they aren't in a nice, even, uniform shape. They took the shape of the container, okay? But they don't fill the whole container. They stay at the bottom. They just take the shape of the bottom of that container, okay? So here we have liquid. kinetic energy is increasing as we move from 0 degrees Celsius to 100 degrees Celsius. Okay, so guess what happens at 100 degrees Celsius? That's where water boils. So water takes more energy to boil than it does to melt. So I'm going to make this plateau a little bit longer. And along this plateau, what we're going to see is that we have not just liquid, but we have liquid and gas. So along this plateau, two states of matter are present. Okay? And what's happening is as we move along that plateau, the liquid is moving. It's not moving, the temperature is not increasing, but those intermolecular forces are being broken. And the water, the liquid water, is escaping into the gas phase. Okay? And we call this phase change either vaporization or boiling. Okay? And what's happening here is our liquid is being converted to a gas. Okay? And this is because, again, we've got another plateau, so the potential energy is increasing. Okay? One thing we should say is the kinetic energy along the plateaus is constant, which makes sense. The temperature is not changing, right? So let's put this over here too. When we melt, the kinetic energy is constant. Okay, so now as we're going along this plateau, we start with almost all liquid, or we start with all liquid, and as we move across, the liquid molecules break free from each other and they go into the gas phase. All right, now once all of our molecules have escaped the liquid phase and they're in the gas phase, if we have our container closed, okay, so that the gas molecules can't escape, okay, what's going to happen now is if we continue to record the temperature is going to start going up again, okay? And this segment of our graph is just, we only have gas present now, okay? So there's no liquid anymore. We just have the molecules in the gas phase, all right? So this last leg is a gas phase, okay? If we are able to measure the temperature and the kinetic energy is increasing again, okay, as the temperature climbs. Now, finally, if I've got my container, like I've drawn my container of my water molecules, okay, remember we've got to have a lid on the container. The gas molecules would just escape into the room. But what we would see if we could break this down and see the molecules is we would see these gas molecules that are spread far apart from each other. And they take the shape of the container and they also take up the volume of the container. So they're going to spread apart from each other as much as they can. Okay, so this is what a heating curve of water looks like. We start below zero, below the freezing point. We are going to add kinetic energy until we get to the freezing melting point. Then we have this plateau where the substance is turning from a solid to a liquid. Okay, we call that melting. And then once we get all of the solid converted to liquid, the temperature, the kinetic energy starts increasing again until we get to 100 degrees, which is the boiling point of water. Okay, once we get to 100 degrees, we're going to have another plateau. Again, this plateau is going to be a little bit longer because it takes more energy for water to go from liquid to gas than it does for it to go from solid to liquid. Okay, so along this plateau, we're converting all of our liquid molecules to gas molecules, all at 100 degrees. And then once we hit the point where all of our molecules are in the gas phase, our temperature, if we keep adding heat, our temperature is going to go up again, and the temperature of the gas is going to increase as those gas molecules are going to spread farther apart and move faster. Okay, so this is what happens with water if we were able to actually see on the particle level as we heat water as we go from solid to gas. So I hope that helps you understand a little bit about what we're talking about when we're talking about a heating curve of water. Have a great day and take care of yourselves.